Okay.
Okay, so thanks a lot for the invitation and the opportunity to talk at this dinner. Let me maybe start by saying that I'm gonna assume throughout this talk that all the schemes are quasi-compact and quasi-separated. So that's an extremely mild assumption. So I want to write this down every time I need it. So the goal of my talk is to study the geometry of mixed characteristic schemes, and especially in the context of base point streams. What are mixed characteristic schemes? These are these schemes that are not defined over a field. So in fact, these are the abstract schemes. So every scheme is defined over spec Z, and some of them may be defined over a field. For me, I'm just going to look at these abstract schemes. So in other words, for example, you could take a system of polynomial equations with integer coefficients and look at the locus divided by them. So imagine you take a scheme over spec Z, and somehow over the generic point, which is Q, this is going to be just like a normal curve. But since your equations are integer, you can take these modulo P and have the congruence modulo P. And what you can get, for example, that your curve is going to split into a union of curves. It's going to be a reducible curve. So one of the reasons that the study of the mixed characteristic, for example, study of mixed characteristic MMP, minimal model programming dimension 2, is important in the theory. So if you don't know what the minimal model program is, that's not going to be so important in this talk. Let me just mention that that's kind of a way of classifying varieties. And so in dimension 2, this minimal model program is important because it allows to construct models of characteristic zero curves with good properties. So for example, this book, Introductory Book to Algebraic Geometry by Liu, that many people use as students. And one of the chapters there is exactly about the minimal model program for mixed characteristic surfaces. Because having you might happen that modulus MP, you're gonna get some really bad curve, and maybe you'd like to correct it so that the model is nicer. So last week, Carl Schwitt talked about our new results on the mixed characteristic model program. So I would like to. So I'm not going to talk too much about that. I'm just let me just briefly recall the result. And sorry, I can't, because of the work on the tablet, I can't see anything. So just ensure, can you hear me?
Yes.
Okay, perfect. Sorry. Okay, so the theorem, Parg of Bats, Linchuan Ma, Jolt Patek Falvi, Carl Schwitt, Kevin Tucker, Joe Waldron, and myself. So the three-dimensional MMP is valid if the residue fields are greater than 5. So we can't work with residue fields 2, 3, and 5. So for example, you could imagine schemes over ZP for P greater than 5, or for example, Z over 130. So here is 30 because 30 is 2 times 3 times 5. So it's exactly kind of removes these residue fields. Okay, so let me maybe make two remarks. So the first one is this is based on So the idea, kind of the strategy, is based on the three-dimensional MMP over a field for characteristic P greater than 5, like Christopher Hagen and Chen-Yang Xu. And also, let me mention, let me go to the next page. He mentioned that some special cases of this result, among many other things, for example, pertaining to semi-stable minimal model program in high generality in every characteristic and all of similarities, is obtained independently by Takamatsu and Yoshikawa. And let me mention that I mean, the MMP kind of for smooth surfaces was known for a long time. Then the general case for mixed characteristic general case in the logarithmic setting is due to Tanaka, and then there were results on a semi-stable mixed characteristic two-dimensional by Professor Kawamata. Okay. So the natural next step to study is dimension 4. And it's not just because it's, you know, not for just for the sake of it. I'm gonna maybe give one application which I think is nice of having MMP in dimension 4. So here in positive characteristics, we have the following result of Christopher Haken and myself. So we show that a 4-dimensional semi-stable MP over a field of characteristic P greater than 5 is valid, assuming resolutions of singularities. And then by semi-stable, I mean is that, for example, you have X over some curve C, and you are going to be very close to some special point, which is S. I look at the special fiber, and I would like the special fiber to be reduced. Simple normal crossing. So that's you may, I mean, you can even assume much more. You can assume LT, and you can drop reducedness, but then you need to state in the correct way that you run in a particular logarithmic minimal program. So let me not go into details. I mean, I think that one of the most kind of, I mean, you focus on this. Okay, and so it's natural to wonder if the same result is true in mixed characteristic, and so this is work in progress. I think hopefully this will be soon out, reasonably soon, by Christopher Haken and myself. Is that the above holds in mixed characteristic? And in a way, the mixed characteristic setting is kind of is kind of even kind of a relative situation. In fact, in a way, more natural in mixed characteristic because everything is relative. In mixed characteristics, so for example, this applies to the case where X is defined, say, over, for example, ZP or any other mixed characteristic DVR, P is greater than 5, and XP is reduced simple normal crossing. Okay, so more or less, the proof is exactly the same as in positive characteristic. If you replace the techniques, the positive characteristic techniques with the mixed characteristic techniques, one developed in our paper with Margav, Lin-Chuan, Jolt, Carl, Kevin, and Joe. And there's one component that is kind of missing, and that's Kashini Tanaka's result of relative semi-ample. So that's going to be I'm going to focus my talk on this on this component that was missing to kind of conclude this work in progress. Okay, so now let me give you an application. So why one would care about 4-dimensional model program? Okay, so if we're, for example, only interested in dimension 3, but X be defined over a field K, of characteristic greater than 0. And I'm going to say that it's liftable if and only if there exists a scheme X tilde flux over some characteristic 0 ring R such that X tilde P is isomorphic to X. So the reduction modulo P kind of is isomorphic to X. So in other words, you can think of these as being non-pathological positive characteristic schemes. So these that to characteristic 0 in a way that they should share a lot of properties of characteristic 0 schemes. So for example, the lineal 0 that these satisfy vanishing theorems, and a lot of properties are satisfied. And these positive characteristic schemes that don't live to characteristic 0, they somehow look like kind of a pathological, they're special to this concrete characteristic. They kind of can be, they're similar. You can't find similar varieties in characteristic 0 with similar geometry. Okay, so it's kind of nice to know which are liftable and which are not. So one thing we try to prove with Christopher for a long time that we can finally hope we should be able to finally prove now is the following corollary. Again, this is in progress. Is that liftability is stable under three-dimensional minimal model program in characteristic P greater than 5. So in other words, if you start with a liftable variety, three-dimensional positive characteristic, then its minimal model is also liftable. And so one thing that one can deduce some additional work out of it is that if you have two Calabi-Yau smooth birational Calabi-Yau threefolds in characteristic P greater than 5, so in positive characteristic three-dimensional, and one is liftable if and only if another is liftable. So in other words, liftability is a birational invariant for smooth Calabi-Yau threefolds. So somehow you can't construct some pathological Calabi-Yau threefold by changing its, finding another birational one, birational to it. Which is so interesting, for example, from the viewpoint of derived categories. So they just that if you have two derived equivalent varieties, then one is liftable if and only if another is liftable. So this kind of shows that just gives more evidence for that conjecture, because we expect by the result of Bridgeland to prove it in characteristic 0 that if you have two birational Calabi-Yau, then they are derived equivalent. And somehow the idea of the proof is not, it's kind of natural. You have one three-dimensional Calabi-Yau, you lift it to characteristic 0, so you have a four-dimensional mixed characteristic scheme. Instead of running the minimal program in positive characteristic, you really run it on this four-dimensional mixed characteristic model. And so what you get when you run this MMP, you get the lift of the minimal model. Or in the case of Calabi-Yau varieties, you have a sequence of flops that connect birational Calabi-Yau threefolds, and you just lift it the sequence of flop four-dimensional models. Okay, so let me just say a few words about kind of the techniques that come into it before I move to the main part of the talk. Let me draw a small table. So I have the minimal model program. I have the work of Heikon and Shu on positive characteristic MMP, and I have our work on the mixed characteristic three-dimensional MMP. And there are kind of we focus on two parts, important parts of the MMP, that is the flips and contraction. So these are kind of the basic surgeries in the minimal model program. Contraction is like taking a subvariety, say a curve, and contracting it, and flip is some kind of a more complicated operation. And in positive characteristic, To construct flips, you use so-called F splittings or F regularity that come from tight closure in commutative algebra. And to use constructions, you use so-called Kills theorem. I will state it in a moment. In mixed characteristic, we use plus regularity. It is based on the result of Bargham's pattern on the integral closure of R and Cohen-Macaulayness. And to do the contractions where you mix characteristic, Kills theorem, which again I'm going to talk more later. Let me just maybe say that what stays behind both notions is Frobenius. So this map that raises each function to its p. And it's really nice in positive characteristic because it's not multiplicative, it's additive. It's really a map of ring. But that's not the case in characteristic 0, nor in mixed characteristic. So the way you kind of avoid go around it in mixed characteristic when you deal with cross regularity, you construct like really huge rings that either have Frobenius or maybe like C shade of Frobenius. So like, and there are these perfectory rings, here you take this absolute integral closure, and they kind of behave there is like really a Frobenius. This is really kind of useful for this construction of flips. But the case of construct, kind of the idea is in a way more naive. So instead of kind of a constructed ring on which there is some kind of like a shadiness, you can think, okay, what is Frobenius? It's raising function to the power. So now let's use it again, right? I mean, it's not additive, but it turns out that it still has at least some additivity mixed characteristics. So I'm placing the Frobenius by just this kind of a naive raising to the fifth power. It's kind of useful in this context. Maybe let me see all these results. I'm going to talk about, and that's going to be kind of the main object of my talk, and study of these contractions and mixed characteristic Kill and what kind of grows out of it. Okay. So the definition, I'm going to say that a line bundle L is semi-ample if and only if some power of it base point free for some m greater than 0. And I'm going to find the exceptional locus. So if the line is semi-ample, that should be exactly the exceptional locus of the associated morphism. But we want to have it defined for every nef, a line bundle, so such that L C is greater or equal to 0 for every curve C. And that's going to be the union of integral subschemes V in X on which L is not big. So in other words, one can say that the highest intersection number after restricting to V is positive. And we take a union of it. And this celebrated result of Kiel is the following. If you have a projective scheme X in positive characteristic, you have an F line bundle, then L is semi-ample if and only if L restricted to the exceptional locus is semi-ample. And usually of lower dimensions, so it allows you to kind of study semi-ampleness, kind of a drop the dimension when studying the semi-ampleness. So let me give you an example, which of course you can do this in many different ways. I just kind of show you a very baby case in which you can use it to show a statement. So I'm going to have a curve which is just P1, and it's going to be contained in, for simplicity, let's be a smooth surface in characteristic P greater than 0. And assume that self-intersection is negative. Then I claim that you can contract C. So there is a map Fx to Z which contracts exactly C. Okay, so let's give a proof of this statement using Kiel's theorem. So it goes as follows.
Jakub, by the way, sorry, do you mean that the E of L is the subvarieties where L is not big? What you wrote is that L is big. You know, in definition of E of L?
Oh, sorry. Yeah. Sorry. Thanks. Yeah. Oof, yeah. Thanks a lot. Okay. So now I'm going to pick a ample, and I'm going to pick two numbers, n, m, which are natural numbers. So that if I pick a line bundle L, which is going to be equal a to the power n, and shift by mc, then I pick this m and m so that L times c is 0. So I know that a times c is positive, is ample, and c squared is negative, so I can always find such positive natural numbers with this property. And unfortunately, I'm stuck in the middle of a page, so let me, remind what's going on, but let me go on the next, write what I want, and then go back here. So now I can notice the following. So the exceptional locus, so my curve L, sorry, my line bundle L is 0 on C and is positive on every irreducible curve different than C. So the exceptional locus is equal exactly to C, and C is P1. And every line bundle is semi-ample base point free, in fact, on P1. So now I can apply Kills theorem to deduce that L itself is semi-ample. And then from this, I get that there exists an associate, a fibration X to Z is exactly defined by some power of L, where K is divisible enough. So again, I want to contract C. I'm picking some N and M so that A N shifted by MC is 0 on my curve and it's positive on the other curves. And I just need to show it semi-ample, which follows from this theorem. As described here, because their relation to the exceptional locus is semi-ample. And let me point out that if you put a little bit more effort, and if you work over a finite field, a closure of a finite field, in fact, show that any curve at intersection is contractible, which is not true in characters for other fields, for example, in characteristic 0. And let me point out that Hill's theorem is false in characteristic 0. You really can't, but I'm going to maybe mention this in a moment. So this Hill's theorem is not only useful for studying base point freeness, but it's useful in many other contexts. So it was initially developed by Kiel to study the line bundles on moduli spaces. It is used in analytic geometry for the projectivity of the vector Grassmannian by Bargav Bat and Peter Scholze. Is essential in the positive characteristic minimal model programming by rational geometry. It's even used to of Manford conjecture and and so on and so forth. So a little bit of that's going to become so it seems natural to have a mixed characteristic variant there. So for that, the following theorem. Sorry. Theorem of myself. So you have X over S, where S is Noetherian and Noetherian, and this is a project X is projective, and L is nav. Sorry. L is nav, then L is semi-ample if and only if L restricted to the exceptional locus and L restricted to characteristic 0 are semi-ample. So this assumption is really necessary because we know it's false in characteristic 0. But somehow it's a relatively benign, because often when we use Kil's theorem, we know that things are okay in characteristic 0. For example, by vanishing theorems or analytic methods or so on. So it's really kind of extending to mixed characteristic that is interesting. And here XQ, let me just maybe define it, is the same as X times spec Z spec Q. And like, since I want to talk about relative semi-ampleness, I won't have time really to tell you more about the proof. But as I said, kind of the very naive idea is to kind of do the P map regardless of the fact that it's not additive. So I call this technique a mixed characteristic multiplicative perfection. So maybe make a few remarks, but to avoid maybe writing too much, I wrote it down already. So I want to make a few remarks. So firstly, Birkar got a variant of the Kills theorem over any field. So his statement that L is semi-ample if and only if L restricted to some thickening of the exceptional locus is semi-ample. And he used this to prove conjectures on the so-called augmented base locus B plus L. So this is useful, for example, for this kind of statement. Unfortunately, for say studying of base Petrinus, it's kind of harder to apply it. So the difficulty is that it's usually hard, even if you know some line bundle is semi-ample in the reduction of a scheme. It's not clear how to extend it to its thickening somehow. And we also mentioned that Liam extended this Birkar's result to mixed characteristic using some mixed characteristic techniques from my paper. Okay, now let me maybe mention briefly some other applications of these techniques that come out from this kind of this multiplicative mixed characteristic correction and stuff. So the first one is a generalization of Kolar. So let's take a separated scheme of finite type over an excellent scheme S, and let's take finite equivalent, which is set theoretical. I don't want to define what theoretical is. If you assume that the quotient exists in characteristic 0, then it's going to also exist in mixed characteristic. It might be an algebraic space, but usually that's not a big deal. So Kolar proved originally in positive characteristic just without this assumption here, just saying that in positive characteristic these quotients exist. So when you think about it, imagine having a variety scheme and you pick 2 points and you want to glue them together, or maybe you pick 2 curves in your scheme and you want to kind of glue them together. So that's kind of this state. Again, it turns out it's in characteristic 0, and we have another assumption of this type that if we knew it was okay in characteristic 0, then immediately we extend it to mixed characteristic. Okay. Then one can also get a new proof of the existence of quotients by proper actions of smooth affine group schemes. So so in other words, I have a scheme, I have some GLN or any other like smooth affine group scheme acting properly on my scheme. And this was known that such quotients exist in the analytic setting for a very long time, and it was brought to the algebraic setting in characteristics by Popp in 70s. Then Kolar extended to positive characteristic and also to mixed characteristic for reductive schemes, which then allowed to construct moduli spaces. And soon thereafter, Kilmore gave a the famous much general result about the existence of quotients. Somehow, using these techniques, one can take Kolar's proof and remove this assumption of reductivity of the group scheme. So of course, it's still weaker than Kilmore, but I still found it interesting that somehow Kolar's techniques can make work in kind of a full generality of these ideas. And also smoothness relaxed, but maybe let me not go into it. And the last thing, which I don't know whether it can be done or not, but I hope that maybe, is the geometric proof of Mafia's conjecture. So the Mafia conjecture says that if you take a finitely generated ring and you take the ring of invariants, some reductive group scheme, then it's going to be this ring of invariants is going to be finitely generated. So that's kind of a basis of the geometric invariant theory. This is very easy in characteristic 0, so the real difficulty is positive and maybe in the mixed characteristic. And it was eventually settled by Habush in the characteristic using representation theories, using this Einberg representation. And then Seshadri, using this technique of Habush, he extended also into mixed characteristic. But what happens is that before Habush's proof, Seshadri had set up a program for showing Manford's conjecture in a purely geometric method. But somehow he could not make it finish, and then Habush's result came in. But many years later, after Kills analysis result, Seshadri realized that this Kills result was an existing component he needed to kind of make his program work. And so together with Seshadri, they made it work in positive characteristics. So it's kind of purely geometric proof of Manford's conjecture. And they wrote in their paper that if only did have like a characteristic variant of theorem, you would have been able to probably do it in mixed characteristics. So that's my hope that somehow in view of that one hopefully can also get a geometric mixed.
May I say something?
Sure.
I am van der Kallen, and the Seshadri's result has quite a bit of restrictions. And with Franjou, I have given a quite general result, but it's not with geometric methods at all. It's with representation theoretic methods. So that's what I wanted to say.
Well, maybe another comment is that actually Seshadri wrote this proof of Mumford's conjecture using this method earlier, and then this paper with Shastri was written with all the details, but there was this earlier paper of Seshadri alone.
No, I'm not worried about that. I mean, our result is from this century. I mean, we're not going to argue about the priority, but
sorry, I wasn't talking about your. I was simply saying that Shastri and Seshadri appeared after another paper of Seshadri that contained the proof using Kill's theorem.
Yeah, but I'm just saying that Seshadri's result, it has restrictions on it, which have been removed since. So the base is now a general Noetherian ring.
You mean without any universal Japanese assumptions?
Yeah, absolutely. And the reason that there are no such assumptions is that the proof is easier.
So thanks a lot. That's it's very helpful for me too, and I look into it. Maybe let me continue with the talk. Let me maybe go back to now. Go to the main main thing I would like to talk about. So this is the relative semi-amp. The following theorem of Kashini-Tanaka, which I like a lot, which says the following. So if you have a projective morphism of excellent schemes, in positive, defined over a field of positive characteristic, and you take a line bundle L is line bundle, such that its restriction to every fiber is semi-ample. So for every point S, small s on big S, restriction to fiber is semi-ample. L is relatively semi-ample. In other words, it's semi-ample affine locally over the base. So if you restrict to some affine neighborhood of some point on the base, then the line bundle is going to be semi-ample. And as before, this is very false in characteristic 0. How you may have a birational maps and a line bundle restriction to the exceptional locus is semi-ample, but somehow it's not semi-ample on some thickenings of the exceptional locus, and it won't be ample on the whole space. And apart from the fact that I think this is like a fundamental result from the philosophical point of view, that it kind of describes behavior of semi-ampleness in families, also very useful in practice. So some kind of like a low-dimensional case of this theorem was proven, say, work of Joe Waldron and kosher recurrence of Mori fiber space. And it seems that like if one would like to extend that to higher dimension, I'd really like need to use the result of Kashini and Tanaka. Similarly, we also needed this in the 4-dimensional minimal model program. This work together with Christopher. Okay, so the result I would like to end this part of my talk with is the characteristic variant, because that's exactly what we needed to finally conclude 4-dimensional semi-stable MMP mixed characteristic with Christopher. Okay, so theorem, and let me call it a star theorem, which means that it's written but it's not on the archive yet. Hopefully it will be soon. Not on the archive yet. So I have fx2, which is a proper morphism of excellent scheme. And I take a line bundle L. L is a line bundle such that L restricted to characteristic 0 is semi-ample, and L restricted to each fiber is semi-ample is of positive characteristics. I take all points on S whose residue field have positive characteristics. And now this then implies that L is relatively semi-ample. And again, one can't get exactly the statement of Tanaka because it's all characteristic 0, so we really need to assume that in characteristic 0 everything is fine. So in particular, this gives us the following. So let me just write it down maybe in some like basic generality. So if you have a scheme X over ZP or some maybe mixed characteristic DVR, which is proper, this is semi-ample if and only if L restricted to the characteristic P fiber and L restricted to the characteristic 0 fiber are semi-ample. In other words, in a way, this semi-ample characteristic kind of theoretically just splits into the positive characteristic story and the mixed characteristic story, and kind of there's no data in mixed characteristics. Of course, in practice, you still need to work in mixed characteristics because the geometric might lie in mixed characteristics, so we still like usually just compose it as easily. But somehow, just for this notion, is just checking semi-ample in positive characteristic and characteristic 0 is enough. And maybe I should also say that it really essentially uses this mixed characteristic Kills theorem. So I don't think there's a way to kind of avoid using this mixed characteristic Kills theorem to kind of prove this kind of state. Okay, so to explain going on here, let me just explain what's the idea behind the proof of this result of Kashin-Tanaka. So there are 3 steps. So step 1 is assume that F has geometrically connected fibers, just connected fibers, and assume that L restricted to each fiber is trivial for every point on the base. Now, this is positive characteristic. Yeah, I'm just recording the positive characteristic story. And then one can show that in fact this L descends. So some power of L is a pullback of M. So for some natural number N, and for M, which is some line bundle on the base. So in other words, if you have a line bundle that is trivial on the fiber, then it descends down. And again, it's kind of like a nice thing, and it follows in characteristics here. Step 2 is to show theorem when X is normal. So in full generality, but for X normal, and step 3 is the general case. And let me be mentioned that in this case is the step 1 was originally proven by Bat-Scholze in their work on the projective lead vector Grassmannian, and it is slightly more general variant for vector bundles. So I don't want to write this down. Somehow, you can't take a multiple of a vector bundle. So the statement is that you have a vector bundle that is trivial on each fiber, then up to perfection. If you in fact take perfection, then it descends down. Okay, so now let me just maybe mention what kind of ideas come into the proof of each case. So step 1 was descending line bundles if you are trivial on each fiber. So add 1. So first you use something which is called flattening. So there is a way to make every morphism flat using birational modifications, and then some form of an intricate gluing of semi-ampleness. Now, in step 2, you use Kills theorem. Alterations sorry, maybe let's look at this step one. So the point is that if the map is flat, it's usually simpler to descend. Some kind of a, you make the map flat, you descend, but then you need to go back, and that's intricate gluing comes into the picture. Now in step two, it's kind of a descending semi-ample is much simpler in the normal case, and so you use operations to do it, and you use Kills theorem to, I mean, either you're big and you're fine, or you're not big because you can descend to a lower dimension in lower dimension use induction, or you're not big, but you kind of can construct like at least a partial map to something of lower dimension. Then you play a little bit to descend there and then use induction. So Kills theorem alterations in step one. And now part three, use the following. So first, we're going to reduce to the normal case. We take the normalization. Then use step to construct vibration for the pullback of L. And still there is normal. So I know the theorem for normal one. And now to kind of go back to the non-normal case, you can take a quotient by equivalence relation that defines the normalization. So normalization, you can construct the scheme for normalization by taking a quotient by finite equivalence relation. So take quotient by x tilde times x tilde over x. And for this Collar's result I mentioned earlier on the existence of finite quotients. Collar's result. So you see, you can kind of construct this vibration of the normalization. Then I mean, you need to put more effort. You use step one and step two again, but somehow I hope the idea makes sense. That somehow you did by taking these quotients, you can then construct this vibration for x itself. Okay, so the mixed characteristic proof. So in the mixed characteristic proof, steps 2 and 3 kind of are analogous to what Pablo and Hiromu did. You're just replacing the Kills theorem and Collar's theorem, their mixed characteristic variants I talked about earlier, the mixed characteristic Kills and Collar's theorem. As for step one, the issue is that it's already quite technical and involved, and somehow trying to replace the Frobenius with these techniques from the mixed characteristic Kills paper, although maybe possible, I would add another level of difficulty and make it even more kind of more difficult to do. So what I did instead, I kind of followed this alternative approach by Bargaf and by Peter. And in fact, mixing it with the more elementary variant thereof, which is written by Johan de Jong on Stack's project now. And somehow this variant, it doesn't need some like derived algebraic geometry, and it's kind of easier to use. Okay. So I would need to spend much more time to really tell you more about this one. So I just would like to focus on one important aspect of it that I think is interesting by itself. That's kind of a preservation of almost blow-up squares for the Picard function. So let me go on the next. Are there any questions, by the way? Okay, so if not, let me talk about that. Okay, so one of important results, the work of Bargaf and Peter. Okay, so I'm going to take F, which is a map from X to Y, which is a projective morphism defined over a field of positive characteristic. And I would like this morphism to be an isomorphism outside some closed subset Z in Y. and I take to be the inverse image set. So this is called like an almost blow-up square. So let me just draw a picture. I have y, I have x, and this is an isomorphism outside of z and outside of E. Okay, so now the statement is that then the following diagram is Cartesian. So I'm gonna take, pick, curly pick, I'm just gonna, of y, and I'm inverting p, curly pick of x, and I invert p, curly pick of z, inverting p and curly pick of e. Inverting p. So by the inverting p, I just mean I identify line bundles whose some big ETH power is the same. What's going on here? And now this diagram is Cartesian. Now I need to emphasize that this pick is not a group of line bundles, it's the groupoid of line bundles. And I'm going to explain in a moment why this is essential. Like this is false for the Picard group pick. Sorry, I'm going to write pick, curly pick, and non-pick differently, and I hope you will see the difference. But yeah, I will try to emphasize that over and over again. So I also need to explain what Cartesian means in this context, kind of like Cartesianity. But like I'm just going to talk about it in a sec. So let me also mention that this is a base of the following result that Bargath and Peter showed, is that this pick and then inverted p is an H stack. So normally the Picard groupoid is an FPPF stack for the flat topology or so on. But there is more general topology constructed by Vojevodsky, the study of Milner's conjecture and motivating things, and somehow this notion of the H topology and H stack is really useful in this context. So this language really allows to make things much clearer. But I don't want to define this. Just mean, let's say this topology is generated projective surjective maps and flat maps. But what is really, the key thing is exactly this result, which more or less says the following: to understand line bundles on Y, if I have this kind of an almost like abstract blow up, to understand line bundles on Y, I need to understand them on X. I need to understand them on the non-isomorphic locus and how they glue on E. Okay, but to make sense of it, I should probably recall what a groupoid is and how we make Cartesian products. So a groupoid, let me remind the groupoid definition. A groupoid is a category in which every morphism is an isomorphism. Okay, to give you an example, I'm going to go to the next page. So to give you an example, is this curly pick. So these are objects, curly pick on X. Is objects line bundles and morphisms are isomorphisms. Of course, I can't say a set of line bundles. I should say a collection of line bundles because there's no set of all, and so on. Let me not go into the set theoretical issues. And now to construct the Picard's group pick X, I just take this Picard group and I quotient by the all isomorphs. Okay, what's going to be essential is constructing products. So say I have two maps of groupoids, C and B to D, called G and H. So these are morphisms of groupoids. So now the The Cartesian product is taken inside the two category of groupoids, but we can write this down explicitly. So at least let me write down the objects, and the morphisms are natural too. So objects are triples C, B, and phi, such that C lies in C, B lies in B, and phi is an isomorphism between the images of small c. This is small c. Sorry, this is small c, and small b in D. See, kind of in the topological setting, you think of this that you have like a pairs of elements on C and B, and then you have a path on their image in. So let's do an example. Assume you have some spaces X and Y in some big ambient space W schemes, sorry. And now if you take the curly pick of X times over the curly pick of X intersected with Y, I mean, I need to add a few assumptions, but let me not do it. Pick of Y, then this is isomorphic to the Picard point of the union on X and Y. So for example, if X union Y is just two copies of one, so X1 is one copy, Y is another copy, then what I'm saying is that to define a line bundle on this cross is the same as defining a line bundle on one P1, define another P1, and also defining a transition function on the intersection. There's on this intersection, a transition function is some number. So some kind of, you can glue them by multiplying this by this particular number, you're gonna get a different line bundles. So this is false. This is false if I use Picard groups. Like to find a line bundle on the union, I not only need to specify the line bundle in each component, I also need to specify the isomorphism that glues them on the intersection. And this is the same phenomenon that happened earlier. Let me go back here. I'm specifying a line bundle on X and a line bundle on Z that kind of, and not just that they glue on E, but I'm also specifying the isomorphism. Okay, so I wanted to explain that before I go a step further. So now the question is, what is the generalization of that to mixed characteristic? Let me write down the statement. Theorem, again, it's not on the archive yet, it's written down. So the result, so I now define pick underline M. Okay, let me just maybe do it this way. So the above result of Bargaf and Peta holds in mixed characteristic if you replace the Picard functor by the following functor. So I'm gonna take curly pick of X M tensor Q, where now M is a line bundle on a characteristic zero fiber. And what I do is this is the same as the homotopy fiber over M of the map of the groupoids, pick of X to pick of XQ. Now I'm tensoring. And let me maybe explain what it is explicitly. So this homotopy fiber is the same constant. I don't just take line bundles that are trivial on characteristic zero fiber. I also remember this isomorphism that makes it trivial. And so I take L is a line bundle on X, and I take a phi, which is an isomorphism of the restriction to the characteristic zero fiber, together with line bundle M. And I tensor it. Okay, in particular, let's maybe write this down for the trivial line bundle. That is just as like the objects of the group are pairs such that L is a line bundle on X and phi is a trivialization of this line bundle. And this, you can use this result to show that this pick M tensor Q is an H stat. Maybe just me remind you. So I have this functor. Sorry, this is underlined. I defined for you. So what I'm saying is that if I go back to this result of Barga, I mean, this statement is true in mixed characteristic. You replace this big inverted P with this more complicated functor. It preserved the abstract blowup squares are preserved. Okay, let me make a few things about the proof. So the proof is based on. So I mean, significantly, the strategy is exactly as in Barga and paper, and also motivated by de Jong, and also the ideas from the mixed characteristic paper, mixed characteristic field, and there is also a baby case of Dokan correspondence. So what's nice about this approach of Barga and Pater is that, I mean, so in my case, I only care about kind of a two categorical phenomena. But somehow their idea has this higher categorical word, and in some situations that really helps see certain things that one wouldn't see before. I mean, there are these cases when, like, I was wondering if something is true or not, and somehow you could followed by abstract nonsense from this infinity categorical word, and I would be a little bit afraid of using this result directly, because I mean I might it's hard to make sure that you check all the assumptions, but somehow knowing that something is true, then it's much easier now to say find more elementary proof if you know that something must be true. So it's kind of nice to see that some kind of this higher categorical phenomena at least slightly touch on something that is more geometry. So let me finish. I'm going to take, if you don't mind, 2 more minutes because there was a slight delay at the beginning. So let me finish with the fact that this theorem is also, there's also a second, there's another proof of this theorem, at least for trivial. In fact, it precedes this proof I wrote, and possibly it could also work for all times, but we're not sure yet. We need to think a bit more about this. It also follows from the following: by taking determinant, this is the result that we observed at MSI 2 years ago, together with Piotr Achinger, Manto, and Akil Matthew. Sorry. And myself. So the above holds, the above result, again, this preserved almost blow up squares, holds for the following functor. So you can take the homotopy fiber, but of K theory, from Kx to Kxq and tensor by Q. And this is this higher K theory extending Grothendieck's 0, so higher K theory. And just say a few words, there's kind of this idea to use homotopy fiber also in the context of PIC. It really kind of comes from this conversation with my co-authors. It's kind of it's a very simple idea, but somehow, it's a very natural idea for topologists somehow, but it was not clear to me at that time that it's a good way to think about that, about such things. So that was like really essential to chat with them. Okay, so maybe let me finish by saying that so now the interesting thing is how kind of these two proofs compare. So I'm not very strong in neither like derived algebra geometry nor K theory. So it took me some time to kind of dig what is really going on behind this proof. Especially in this K theoretic proof, we use a lot of like statements, of other people. As far as understanding what's going on there is that somehow one uses this notion of a derived blowup, and it turns out, I need to spend more time thinking about it, but it seems like this it seems like it's extremely powerful. In a way, it allows you to understand blowups along arbitrary centers by understanding blowups along centers defined by regular sequences. And this seems, if you are allowed yourself to kind of work with visual. So there is some kind of possibly more interesting interactions between K-theory and things more geometric. Okay, so that's all I wanted to say. Thanks a lot for listening to my talk.
Thank you very much for the very nice talk, Jakub. Are there any questions?
Yeah. Could you explain how you tensor the groupoid with Q?
Oh. So, I mean, I should have said more. So what I mean by this Q, so sorry, let me go, where is he?
Here it is, yeah.
Yeah, so philosophically speaking, what I'm doing is if I have two bundles that some multiples of them agree, then I identify them. I mean, formally speaking, I'm kind of taking a pairs, like a line bundle and the number, which would correspond to this Q, and then I identify them if, you know, taking a pair of a line bundle agrees with this, with taking a multiple of this number. So that's kind of writes this down explicitly. But the idea is I'm just identifying bundles whose big power is the same in a kind of a two-categorical way.
Are there any other questions? Well, then let's thank the speaker again. Thank you, Jakub. So I will end the meeting here. Thank you all for attending. See you on Thursday. Bye-bye.
Bye, thanks.
Well, thank you, Jakub.